Welcome learners. I am Dr. Pawan Kumar, Assistant Professor in School of Sciences, IGNOU. So today we shall discuss one topic, that is DFS algorithm and its applications. So this topic refers to the course Graph Theory, which is an elective course of the program M.Sc in Mathematics with applications in Computer Science. Of course, the students who have also enrolled in the course Design and Analysis of Algorithms may also benefit from this talk. So let us just start what we mean by the DFS algorithm. So briefly we shall see this algorithm, what are its applications, and then we shall look at certain illustrations using some examples. So let's first see what this algorithm is. DFS stands for depth first search. So DFS algorithm is actually a graph traversal algorithm that is used to traverse or visit the vertices of a graph one by one. So it is one of the fundamental graph traversal algorithms, just like breadth first search. So, but however, the concept of depth first search is a little different from the breadth first search. In depth first search, we start from any root vertex, and then we keep on traversing the graph as deep as possible. And once we cannot move further from the current vertex, we just move back, and then from that current vertex we again start traversing as long as possible. And this process continues as long as there are vertices which are not yet visited. So this was just a vague idea how this algorithm works. We shall formally see the procedure of this algorithm. But before that, let us look at an example. So here is a graph. You can see. Let's start traversing this graph using the DFS algorithm from the vertex, say V1. So we shall use red color for marking a vertex if when it is visited, and also the edges which are used in red color. So from V1 we can move to either V2 or V4. Note that while traversing a graph, we shall always move from one vertex to another only through an edge, that is only through the neighbors of the current vertex. So from V1 we can move either to V2 or V4. But in this graph, let's maintain that we are visiting vertices in the ascending order of the indices of the vertices. So we just move from V1 to V2, and then V2 to V3, and then V4, V5, V6, V7, V8. Now you can see that from V8 we cannot move further. So we just go back to the vertex from where we reached V8, that is V7. So we backtrack to V7, and then again we can see we cannot move further from V7, so we again backtrack to V6. Now at V6 we can see that there are certain vertices which are still unvisited or untraversed, and we can move to them. So we just go to V9, then V10, and then V11. Again we can see that at V11 we can not move further, so we go back at V10 and then V9. One thing that you must note that while backtracking we use the same edge through which we have moved further. For instance, from V10 we could not move to V5 although there is an edge, but we have moved V10 to V9 only because we have used that edge while moving forward. So moving backward will always possible only the same edge. And then V9 to we can move still further to V12. Again from V12 we cannot move further, and then we backtrack to V9. So we have visited all the neighbors of V9, and then we backtrack to V6 again, and then V6 to V5, and V5 to V4, and then V3, V2 and V1. So this is how the basic idea how the algorithm works. It starts from just any root vertex and traverses the vertices one by one as long as possible, and when it is not able to traverse move further from a vertex, it just backtrack to its parent vertex and then continue the same process as long as there are untraversed vertices. So let's now look at the algorithm formally. So the algorithm needs mainly two containers, T and L, where T is just a list that stores the edges of the spanning tree, and L stores the vertices of the graph and in the order they are visited. The algorithm is given here. The basic framework is this. So the algorithm just takes a connected graph G with the root R, and the result is a spanning tree of G rooted at R. So you must know what is a spanning tree. A spanning tree just of a graph is just a tree which is a spanning subgraph of the original graph. So in this algorithm we are just taking a graph G as input graph with the root vertex R, and then the output is a spanning tree of the graph rooted at R. So initially all the vertices are marked as unvisited, and the containers T and L are taken as empty. So once the initialization is over, we call the DFS procedure with the root vertex R. The DFS procedure is given here. It is actually a recursive algorithm. So from the current vertex, say U, when this procedure is called, U is marked as visited, and then for each neighbor V of U, in notation it is denoted as V belongs to NU. What we do, we check whether V is visited or not. So if V is visited, we do nothing, but if V is unvisited, then we need to perform certain actions, and what these actions are: add the edge UV to T, append V to L, and again we call DFS procedure now from the vertex V. So you can see that the procedure calls itself recursively. So the same process starts from V now, the current vertex becomes V, and this procedure continues. So when will this algorithm terminate? Surely if for any current vertex U, if we could not find any vertex, any neighbor of U which is unvisited, so in that case this loop will not work, and we will reach to the end of the algorithm. So the algorithm is described now formally. Let's look at one example. So we are given one graph here. So let's start traversing this graph from the vertex V1. So initially we have L equals to empty and T also empty. Now when we start with V1, L contains V1, and then we move to V2. So we can see that when we are moving from one vertex to another, the spanning tree is also updating. So V1, V2 is included to T, and then V2 to V3. So again this edge is also added to T, and then V3 to V4, V4 to V5, and then V6, V7, V8. Now we cannot move further from V8, so we need to backtrack. So we just go back to V7, and then same case is here, we cannot move further, so we go to V6, then V5, V4, V3, V2, and finally to the root vertex V1. So you can see that the edges shown in green color are essentially the edges of the spanning tree, which are listed here. V1, V2, V2, V3, V3, V4, V4, V5, V5, V6, V6, V7, and V7, V8. Let's look at one more example. Look at this graph. So here the vertices are just alphabets. So in this graph, we shall visit them in the lexicographic order, that is in the dictionary order. So again, let's start with the root vertex A. So initially L is A and T is still empty. So we move to B. So AB is included in T, and then B to C, C to D, D to E, and then H, and then J, and then we cannot move further from J, so we backtrack to H, and then G and F, and then again we backtrack from F to G, and then G to H, H to E, E to D. Now at D we still have some unvisited vertex, that is I, so we move to I, and then we backtrack D, and then C, E, B, and then finally the root vertex. So the spanning tree that we have obtained in this case is the shown in green edges, which is the edges AB, BC, CD, DE, EH, HJ, HG, GF, and DI. So you can see that the algorithm DFS is very fast and very simple, intuitive approach of traversing a graph. So one thing, this algorithm has many applications, and in this session we shall discuss one particular application, which is about fundamental cycles. The algorithm, due to the linear time complexity of this algorithm, it is vastly used. For instance, it can be used in finding the cut vertices of a graph. It can also be used to find the blocks of a graph, and of course in finding the fundamental cycles of a spanning tree. So in this session we shall only talk about one particular application, that is the computing the fundamental cycles. So here let's first define what we mean by a fundamental cycle. So let T be a spanning tree of a graph G, and UV be an edge of G not lying in T. Then the unique cycle in T plus UV is called a fundamental cycle of T with respect to the edge UV. So you may recall that since T is a spanning tree, it has no cycle. So if you add one more edge to this, we will get exactly one cycle. So this unique cycle is called the fundamental cycle of T with respect to the edge. So we shall see how to find fundamental cycles using DFS algorithm. We shall see a slight modification of DFS algorithm to get fundamental cycles. So let's take an example here before looking at the application. Look at this graph. You can see that the green edges form a spanning tree in this graph, and the edges that are black are not part of the spanning tree. So for each of these edges we can find one fundamental cycle. For instance, if we look at the edge V2, V5, then the fundamental cycle of this edge can be constructed by looking at the path from V2 to V5 in the spanning tree, and this path is shown here, V2, V3, V4, V5. So using this unique path and the edge V2, V5, we get the cycle, the fundamental cycle of V2, V5. Similarly, you can find the fundamental cycle of V8, V9 and it is constructed by the path V8, V5, V4, V9 along with this edge V8, V9. Similarly, you can find the fundamental cycle of the edge V1, V6. So for this edge, you can see that the fundamental cycle is constructed by the path that exists in the spanning tree from V1 to V6. And what this path is? This path is V1, V2, V3, V4, V5, V8, V7, V6. The paths shown in red edges. So this path along with V1, V6 gives us a fundamental cycle corresponding to the edge V1, V6. You can see that every edge gives one fundamental cycle and exactly one. So this gives us tells us a very question. You may like to answer this question: how many fundamental cycles of a spanning tree T are there in an n vertex connected graph G with size M? So one thing that you need to know is that since T is a spanning tree, so T has n vertices, right, and hence n minus 1 edges. But the graph has m edges. So how many edges are remaining? That means the edges which are not in T. So there are m minus n plus 1 edges, right? And for each of these edges there exists a fundamental cycle. So there are total m minus n plus 1 fundamental cycles with respect to the given tree T. So now let us come to the algorithm that finds the fundamental cycles of a given spanning tree. So the algorithm is shown here. It just takes a connected graph G with the root vertex R, and its output is a rooted spanning tree TR along with all the fundamental cycles of TR. So as in the case of DFS algorithm, we just mark all the vertices initially as unvisited. Here we take three lists: T, T bar and parent. T is just the list which contains the edges of the spanning tree. T bar is the list which contains the edges not in T, right? That means that edges not part of the spanning tree. And parent is an indexed list, so it just stores the parent of each vertex. So initially T and T bar are empty and parent of R is also empty. The root vertex has no parent. So once this initialization is done, we call DFS R. This DFS is slightly modified. We shall see what this modification is. So once DFS R is called, what we get? We get the list of edges of the spanning tree T and T bar and an index list parent. So now once these things are there, we for each edge UV of T bar, we just find the unique UV path P in T, and this unique path P along with the edge UV gives us the fundamental cycle. So we just print the cycle P plus UV. So this will give us all the fundamental cycles of the spanning tree T. Now let's look at what this modified form of DFS procedure is. So it is given here. So suppose DFS is called from the current vertex, say U. So U is marked as visited, and then for each neighbor V of U, what we do? There are two cases. Either V can be visited or it may be unvisited. So if V is unvisited, that means we need to visit it, right? So in that case, we shall add the edge UV to T, because we are using that edge for traversing from U to V, and we just mark U as the parent of V, right? Because we are moving from U to V, so U is the parent of V, and then we call DFS again now from the vertex V. So Now this is the first case. If V is visited, what we do? We shall check if V is not the parent of U. So in that case, we shall add the age UV to T bar. Because V is not the parent of U means we have not used the age UV in the while visiting the graph. So in that case, UV becomes an age which is not part of the spanning tree. So that is added to T bar. So this procedure continues as long as there are unvisited vertices or all the vertices are not yet visited. So let's look at an example how we can compute the fundamental cycles. So here is a graph. You can see that the graph has 7 vertices. Again, let's start with the root vertex, say V1. So we are on the right hand side, you can see a table which just stores the parent of each vertex. So here initially V1 is the root vertex, so it has no parent, it is empty. So we move from V1 to V2. So we mark V1 as the parent of V2, and then we move from V2 to V4. So then V2 is marked as the parent of V4, and then from V4 to V3, V3 to V6, and then V7, and then V5. So you can see that while visiting the vertices, we are also keeping track of the parents of all the vertices. So on the right hand side, we have the parents of all the vertices except the root vertex. So, and this information will help us construct the fundamental cycle. For instance, now there are 4 edges which are not part of this spanning tree, and these edges are V1, V3, V2, V5, V4, V5, and V4, V6, right? So for each of these edges there is a fundamental cycle. And how to get these fundamental cycles? Suppose let's consider the edge V1, V3. So for this edge there exists a path in the graph, in the spanning tree. Now how to get that path? That path can be obtained using the information about the parents of the vertices. So for instance, let's look at V3. So we know that V3's parent is V4, so we can move from V3 to V4, and then V4's parent is V2, so we can move from V4 to V2, and finally V2's parent is V1, so we can move from V2 to V1. So in this way we can get the path from V3 to V1, and in this path if we add the edge V1, V3, we get the fundamental cycle. Similarly, if we just look at the path, the edge V2, V5, so then in that case the unique path in the spanning tree is V2, V7, V5, V7, V6, V3, V4, V2. Okay, this path. So using this path, we can just see the parent of V5 is V7, and then V7's parent is V6. So all these information can be used to get this path, and this path is now added with the edge V2, V5 to get us the fundamental cycle of V2, V5. Similarly, you can compute the fundamental cycle of V4, V5 and the edge V4, V6. So in this case, so we can see that this is very easy to compute the fundamental cycles. Fundamental cycles are quite important for many structural properties of graphs. For instance, we can understand if we know we can understand the whether the graph is bipartite or not by using the information available about the fundamental cycles. There are many interesting results which use this information, and so this was the one of the applications of DFS algorithm. There are many other applications which are not possible to discuss in this small session, but there are surely we may discuss them in some other session. So let us briefly see what we have discussed in this talk. We started with the depth first search procedure, and we described it through examples. We have seen how this algorithm works and seen that what is a fundamental cycle of a spanning tree and how to compute the fundamental cycles with the help of DFS algorithm. So that was all in this session. Thanks.